All right, class. We just finished talking about vacation trips here. So kind of now ready for the class itself here. So looking at the schedule, I just gave you back your exams. We have till Friday to do corrections, and then we'll go over them. And we are going to finish up chapter 3 before we hit the rest of before we finish off the semester. Now let's see what's a few things on the calendar, and ask me please here. Let's see a few things. There's a written final on the 26th. There's also something called a verbal final. Oh man, yes, torture. Love it. And so it's going to be a certain set of homework problems that you have already done. And in essence, what you're going to do is you're going to teach the class the homework questions. So essentially what you have is here is I need enough questions in the database. You do have to memorize them. You do have to kind of present yourself to the mirror, right? And practice doing them. And then you present them in class. It is a random selection. I get to randomly select whichever question I like. And you come up to the board and you do it and you explain it to the class. And I'll demonstrate as well before we get there.
Randomly select in class?
In class.
That day?
That day.
How many people are there?
As you come up to the board, I select which one we're going to do.
But you're giving us.
And
know which ones they're going to be out.
yeah, you are going to know already. But
It's just any problem.
Right, yeah. You are going to know what they are in advance, but you just don't know which one I'm going to pick.
Yeah.
So what this is in the European system, in the classical model, is called a ballot system, in which the number of problems should be a cumulative understanding of the whole entire course. We good? So I'm going to kind of do that for you guys. Okay, honor question or honor students, you guys gonna have a bigger list. That's all. So you have a little bit more of a comprehension of things I can pick from that list. And so, and you still don't know, I could pick up the canon question, I could have picked up the honor question. So you can't say like, oh, he's gonna give me the honor question, because it's all just gonna be a random bucket. We're good? Okay, so there's that. So the verbal final, so people that are the guinea pigs are gonna go on the 24th. And or volunteers, and then the ones that say, you know, I'm going to hold off just a little bit here. We're going to go on the 31st. We're good. All right. Then we have something called presentations. So the first time we're going to do presentation, those that want to go, is going to be on the 21st. And so, what is a presentation? Let me hand this out real quick here. Then I'll put it on the board. All right, so what is a product presentation? Here it is. It is you connecting something from whatever algebra we studied so far. So we studied equations, polynomials, quadratic functions here, and we're going to study the exponential functions here. One of two things you guys can go about it. So you either connect it to something that you know in life in general, and like, oh wow, that's so cool. That's something that blah, 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 right? And so then you do a presentation like that. Or as you studied something in the textbook and you're like, I really want to dive into this concept that we studied in the textbook. Okay. And so one of kind of two ways to do it. Maybe some things to start you guys thinking about it here. So if you enjoy history, you can jump into the name. Where did the name of algebra even come from? What? I don't know. Or if you can, you want to look at some kind of development that we've talked about, like where do quadratic functions come from? Why do we use them? When were they actually established and for what reason? So like that kind of thing. The history people in the room here, okay? Analytical people in the room here. Any functions that you've studied that you actually have used in life? Did you ever see, or did you guys use a parabola in life? You know, they are out there.
A presentation on why we don't use math in life.
Oh, interesting. I think I might even accept that. Okay.
How long should this presentation be?
Thank you so much. At the most 5 minutes, like 3 to 5 minutes. Is gonna be very short. 3 to 5 minutes. They're just trying to connect you to
So
things
like
that you
like
studied.
5-minute presentation, do you have a minute per slide or something like that?
Generally feel is, yeah, about maybe 10 slides-ish, 10 to 15 slides. I mean,
Whoa.
depending, you know how slides, some slides go really, really fast, right? And some slides you spend a whole 3 minutes on a slide, right? So it's not how many slides you have, the time is more important.
So just
3 to
like
5
rehearse
minutes
it ahead of
present a
time to make
topic.
sure it's-
Say again?
Just like rehearse it ahead of time to make sure it's.
Yeah, about there. So the way I usually accept them is if you do it in Google Slides, you just send it to me via email. I pop it up on the screen and we're good to go. And if you do it by PowerPoint, and if you want to give me a thumb drive, I can put it right into the slot here and then present it and you're good to go. And I usually sit as one of the students at that point, and then you're presenting on the board. Cool. All right. Those of that are into art. If you've seen algebra in art anywhere, design patterns or anything else like that, astronomy, board games, computer coding, anything. You're good. That's anything that'd be connected here. Sports is also another one here. One person did a presentation on the perfect volleyball spike. How about that? What does it take to actually hit it? What angle? All the good stuff here. Let's see, another one, sports. Best angle for a free throw. There's another one. It's a parabola, and so the equation from the free throw line to how high you are to the basket, and what's that equation? What models the perfect free throw? It's stuff like that. So it's just something that you like. Oh, I do this in life. Is there algebra that connects to it?
Just a quick question. Could we, instead of writing about how we don't use it in life, maybe we write it about why we might not use it in life for the specific jobs that we don't go into.
I want to see that presentation, Noah. So go from there. Okay, so I'm thinking the people that want to go and get it over with, if you want to do that and volunteer to do it on the 21st, you guys may absolutely go for it. And then we'll find out, let's see how long it takes. I'm kind of just going to judge things here. We can even do presentations here as well, right? So I'll put a question mark right here, right? And the 26th would be the written final. Okay, yes. Noah.
This is a weird question, I think, but if you do it on the 21st versus the 24th, is there a difference in credit or?
No, and I'm going to send you guys a rubric as well. What I expect from it, and it's pretty much like a 25-point rubric or something that shows at least what the expectations are. And then also your peers are gonna grade you as well.
Oh, no.
Oh man, she was.
So we can all form an alliance together.
It's just all
Just
all
like
five of them.
Look at that, A plus. You didn't even see my presentation. A plus.
You guys want to form an alliance?
It's like the vibes are immaculate on it. It's great. A plus.
Okay, rubric.
I don't pay attention. It's captured my imagination.
The font area.
Yeah.
All right, let's see.
It was in the font. It was just in the perfect font.
Any questions on any of the schedule? Going once, going twice? No, okay. So let's jam with it. We do have quite a bit to go. Today, which is 3.1. I didn't put the due dates for homework in yet, so I should probably do those as well. So no school next Monday, just so you know. And I think we're good to go with that. And then I think grades are due like right over here, sometime right over here. So grades are due for the first semester. Oh, that's right. So real quick here. I did put in your scores. Did I return your grades yet or no on Google Classroom? Did you guys see any grades returned?
I didn't see.
Okay,
I mean, I haven't checked.
you should have got an email usually.
Oh, I've been ignoring everything.
No, so I have all the grades in there. I just haven't returned them to you guys here. So all the grades are in. So I'm just going to click return, and you guys will see a population of sort of grades. So then at that point, that's all the homework I have. That's everything I have for you guys as of today. We're good. So if you're missing anything, go back to see if they're missing anything. Okay. All right. With that said, let's jam. We're going to take a look at chapter 3, something called exponential logarithmic functions. So far, we've had a roller coaster of rides here. We've learned linear function, right? We learned the quadratic function. Then we learned the exponential functions. And now we've learned the rational functions, which is fractions, right? With the, you guys remember, let's see, I know it's been last year, but vertical asymptote, horizontal asymptote, all the good stuff here, right?
Isotope.
Yeah.
So, and now we get to the last two type of functions that we kind of think about as algebra, right? And so after that comes trigonometry functions here.
Oh, no.
And that's going to be a whole class for next year, those that want to.
What are we doing after this?
So we're going to skip chapters 4, 5, and 6, and we're going to go all the way to chapter 7. And we're going to deal with
I'm not sure.
7, 8, 9, and 10. We're going to skip the trigonometry part there.
Oh, okay.
So we're gonna
Are we
skip.
gonna have the basis enough though?
We're just going to skip that part entirely. We're going to go to all the pre-algebra, pre-calculus
No, I know for
concepts.
that, we're gonna have the basis for that.
Oh yeah, next year. Got a base for that next year, sure. You're gonna. So we deal with chapters 4, 5, and 6 next year. That's what we'll do. Okay, real quick here, let's go for it. Exponential functions and their graphs. And these guys are intertwined together. So you kind of notice that we jump between exponential function and logarithm because there's some kind of connection here. I wonder what it is. So first today is just going to be exponential functions here. On Wednesday, we're going to jump to logarithmic functions. Then we're going to take a look a little more with properties, and then we're going to turn around and start solving all these guys. Solve a whole bunch of these. So let's jam. So by definition, if you want to write it down, 3.1 definition, the exponential function is, and I'm not going to do all of these. I just kind of set up the lecture. I'll skip around just a little bit here and there with things. So 3.1 exponential functions and their graphs.
Also, are you gonna hand out the worksheet today?
I will send you guys the homework sheet. I'll send you guys the homework sheet via email tonight. All right, don't need to write down a lot of all of this here. So maybe just put definition, the exponential function with a base of a denoted by this right here. And two conditions we probably should write down is a has to be greater than 0. You can't have a negative inside an exponential function. And then also a can't be a 1, because if it's a 1, it's actually a linear function. That's it. All right, and a quick little question, raise your hand if you brought your calculator today. Yeah, okay, if you have your calculator, please take it out. You'll need it today. No. Again? Pencil. I do not have a pencil. I have a pen. Oh yeah, please do, yeah, absolutely. Thank you for asking. Okay, we good there? As people are starting writing stuff down? Okay, so by definition, real quickly, if just let's jam with it here. So first things first, if I have a 1 instead of a 2 or 3 or 7, so this is the only condition you can't have. The only positive number that does not work. What's 1 to the second power? What's 1 to the third power? 1 to the fourth. I see a pattern here. So instead of being an exponential function, what we have is we have a constant function. This guy, it just goes straight like this. That's a horizontal. That's a constant function. We don't even work with that. We don't consider that an exponential function.
Can a be -1 though?
Let's try it here. Just a second here. Let me introduce something else. Good question though. Keep those questions. Ask me those questions because this is what we're here for. If you knew this stuff, you would not be here. So next thing, how about if I make a function looks like this? Oh, you know what? Real quick here. This.
What it says, as I am blind.
Yeah, that's what I was struggling with.
Oh, sorry. What did we need? The
I
definition?
think that the screen might-
Oh, yes. Okay.
I don't know. It could be that I'm just blind or it could be the screen.
It's small and a little fuzzy.
It is a little fuzzy.
Did I get blind or did
Yeah.
the screen go blind?
This way.
Did the screen get wild?
This is like when you get blindness thrown on you by a witch in Minecraft.
Okay, that looks okay to me. Is that looks okay to you guys?
Yes.
Right there? Okay. Eyesights are 20/20. We're good? Okay.
The
Definition.
definition.
Even better yet, how about this? No, not that. No better. Okay, so the exponential function f with base a, and it's denoted as f of x is equal to a to the x right here. And then we have certain conditions that a has to be greater than 0. And then a cannot be a 1. We just talked about why a cannot be a 1. Good there, Noah?
What does it say after, we'll have a with base of a?
That says is denoted by,
Okay.
so the way we write it. Okay, good there.
Yes.
And I'll write these things that are kind of like small. I'll write them out bigger since you guys are on the side. Okay, real quick here. Let's start here. 2 to the x. That's an exponential function. That's easy to do. So if I were to punch in a 3, so what is 2 to the 3rd power? Can you guys do this without a calculator? 8. That's easy enough, right? The fun part comes in with exponential functions here. Notice we can only do integer values, right? We can do 2 to the 2nd, right? 2 to the 3rd, 2 to the 4th. The expansion of the exponential function is, I want to do this. I want to do f of 3.1. What is 2 to the 3.1? Oh, brain can't do that anymore without a calculator. We good? So grab your calculators real quickly here.
Wait, it's 2 to what?
2 to the 3.1.
Okay, I also have a question.
8.574187.
5, 7. Yes.
And since it's a third, but it's a negative 3.1, so with the,
So hold on, we're gonna get there in just a second here. So
yeah, so then it is multiple.
I think she's confused all of us, but I don't know if she's right or we're all wrong. Or wait,
So-
no, that doesn't work.
so let's go
I
with it.
was
Let's,
merely indicating something on the board.
uh-huh. She's going next level here. So 2 to the 3.1 is 8.57. Are we good there?
Yeah.
So now let's do A. A actually says, can you find for me f of a negative 3.1? So this is 2 to the negative 3.1. Can you guys give me that answer? Ooh, is it a negation of the 8.57? But negation, like negatives, right? Negatives, if they're in front of the big number, that means negative. But if they're inside the exponent, what does that mean?
Doesn't that mean imaginary numbers?
Well, we're about to find out.
About to find out. So what do we get for the value of 2 to the negative 3.1?
1166291.
0.1162. I'm going to stop there. Yeah. Thank you, Luke. So 0.1162. How in the world does 8.57 relate to a 0.1162? You guys do this on the calculator real quick here. Can you guys do 1 divided by 8.57? Take the reciprocal of 8.57. What do we get?
0.11668.
Yeah, close, yeah, because we have, okay, we have, we're not decimal approximations. Correct. So real quick here, these little negatives inside the exponent, they actually mean reciprocal for us. So it is funny. Okay, we can put a whole bunch of weird stuff inside here now. So notice for C, so we just did A together here. So A, there's that. Abby?
Excuse me, pardon, I've forgotten what a reciprocal is.
Reciprocal,
Please
absolutely.
further explain.
No problem. If 5 is a 5, the reciprocal is 1/5.
Oh, thank you, that's very helpful.
No problem.
Opposite, it's like the fraction.
The fraction, yeah. It's the flip of the fraction.
Oh, wow, got it, got it.
So they're usually called 1/2 or 2.
Yes, absolutely.
Oh.
And
Thank you
so-
for asking that question.
So real quick here, let's do this one here. So really, you say 5, the reciprocal of 5 is 1/5, right? So if I was to write it in terms of equal signs, I would say 5 to the -1 is equal to 1/5. We good? It's just where that negative is pointed at. Okay, do we just ruin Noah's Christmas and New Year's and everything else right now? Okay, so if I have a negative in front of the number like this right here, that means a -5, right? That means opposite along my linear, it's the opposite value, right? Across on a real number line. If I have a negative inside the exponent, it means reciprocal. Good there? And then there's one more. There's actually one more thing I can't tell you. Okay, there's one more where we don't do something called the inverse, but we don't do that yet. Okay,
So is it the reciprocal of 2 to the, or 3.1 to the power? The opposite of 8.5.
so let's do this here. If you guys real quick here, just real quick on your calculator, put 1 over 2 into the 3.1. Can you punch that into your calculator? 1 divided by
0.116629.
sorry, Abby, say again.
0.116629.
Okay, so are you okay with the relationship there?
Yes.
Awesome. So notice, if you guys think about it, notice chapter 2, just one more thing and we'll kind of get going. Notice chapter 2, we dealt with this right here. We dealt with x to the 2 power, right? And everything that happened because of that, that was a parabola, right? That was a quadratic function. We expanded to the x to the 3rd, x to the 4th. We expanded this out to a whole bunch of stuff. That was chapter 2. Chapter 3 says, hey, you know what? What happens if I switch these around? What happens if the 2 goes down here and the x goes down here? That's what we're doing. It's just another question. And then the whole new world opens up to us because we asked that question. Okay, so we're good there. We can do it by calculator. I think we're jamming. Okay. And, oh, I did have it here. Okay. Sure. You guys, thank you so much. I would rather have a conversation and you guys having those questions and we discussing that, because that's, in my mind, that's what real sort of learning education is. I'm not sure why I have this one. I have the blown up version on the next slide here. So I think I changed it up. So I'm not going to do all of these here, just kind of a few as we go. We good? But tell me if you need more time. I'm going to try to get through 3.1 today. We are done at 9:45. Okay.
My brain is real good.
That's cool. Okay, let's jam with. Ooh, this would be a good one here.
This is how I know that I'm never going to use math in my life, because I don't understand it, you know.
You will. So how about this? I'm going to stick in pi. Can you guys, on your calculators, can you actually stick in a pi into the exponent?
That's a pi symbol.
There's a pi symbol in your calculator. You think you have to press the second function to get there.
Oh, I found it. Okay.
Oh, there.
Oh,
Wait.
8.8249.
Ooh, we're
I
gonna
got
go negative pi.
Oh,
it's negative. Oh,
pi.
Negative
I
pi.
got 0.11331473.
If it's negative pi, why is it in the F parentheses?
Oh, yes, thank you. Oh, got it. Because the function itself had a negative inside it from B.
So it was negative x, 2 to the negative x.
Oh, I see. Okay,
Okay.
got it.
Okay, 0.1133. That's kind of what we're looking at there. Should we do that last one? Let's do this one here. C, so I have C is 0.0x. So if we plug in the 3 halves, So let's stick in a fraction. Can we guys stick in a fraction into the exponent here? So 0.6 to the power of 3/2. Can you guys give me that?
One, 4, 6, 4, 7, 5.
Real number as far as, you can't put an I in there, but you could put real numbers, or 3/2 is still a real number.
So. I'm trying to remember how many it's applied at the
Okay. Okay, are we good? So we could use calculators. We actually can use, as long as they're whole numbers, we can use our mind to do it, right? But once you get into decimals and once you get into fractions or pi values, no way, we have to just use a calculator because we're doing almost like, we're doing partial. That's a fun story. Hey, a good presentation, Noah. How do people calculate without calculators pieces of?
There were people called computers before there were computers.
Okay,
Yeah, there were.
sure.
Because they would compute values.
Well, you computer, you compute this.
Yeah, because they compute a value. And so computers replaced them. Because
Okay, guys, let's go with it
they
here.
just did it so much faster.
And some number crunching, but not everything here. No, let's continue real quick here. So I have a function called 2 to the x. What we want to do next is we want to look at what these functions look like. Let's go back to what we know already. Linear functions, right? When we graph linear functions, you guys talk to me, do they look like this right here, right? They kind of look like that. Those are linear functions. Okay. Then we had quadratic functions here, x squared, right? It went like this. Then we had x cubed, and that went like that right here, right? And then we went to x to the fourth. So we have these little, then we went x to the fourth, and those kind of went like this right here, right? So we've had a lot of good functions already that we've been able to graph. Now the question is these exponential functions, what do they do? How do they bend? How do they curve? So since we want to do this kind of quickly here, let's do this here. I'm going to take a, which is 2, and I'm going to probably just use just some real quick ones here. How about -3, -2, -1, 0, 1, 2, and 3? We'll just use those as inputs because I think we can actually see a pattern even. So if I say 2 to the -3, ooh, you know what? Hold on. You guys, we talked about it earlier. So can I do this here? That little negative means reciprocal. This really just means 2 to the third power, but the 2 to the third power is in the denominator. Is that right? Boom. What is 2 to the third power? Anybody? 8. All right. I got 1/8 over here. So a -3 gives me a 1/8. 2 to the -2. You guys talk to me here. I'll do the work. Dun, 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 dun. Oh, not, sorry. I put a 4 in there. Should have been a 2. 2, 2, 1/4. Awesome. 2 to the -1.
1/2.
1/2. Reciprocal of 2, right? Ooh, the fun one here, guys. Ready? 2 to the 0 is
0.
good. 1. All right. Any number to the 0 power is 1. I totally understand. 2 to the 1 power is just a 2. 2 squared is 4. 2 to the third power is 8. And my question is, can you guys graph this for me? All yours. And once you finish, take a look at your neighbors. So you're going to graph a -3. I'm going to go out a little further. -3, -2, -1, 0, 1, 2, and 3. And kind of just graph this on some graph paper there. And again, we're just trying to see how these particular exponential graphs are going to look like. All right, let's see. The highest value for y is 8. So there's no, hey, look at that. First things first is weird. The y values are never negative. Oh, 1, 2, 3, 4, 5, 6, 7, 8. There's 8.
It's infinitely close to the, y0.
As it goes to negative infinity, yeah.
It goes, yeah, it goes to negative infinity, and close to, y0.
Okay, so -3 is 1/8. This is a 1/4, just barely higher. This is a half, so it's halfway up to 1. That hits the 1. Then we hit a 2, and we start jamming. We go up to 4, then we go up to 8. Everything is doubling so fast, right? Each time we scoot over, it doubles. Hey, I wonder why the 2's there. I think that's what it means to double. Okay, so what does this graph look like? It gets infinitely close to the x-axis as it goes to negative infinity, but then it has a slope curve. So that's funny. So it's almost like a parabola, but it's flat on one side, isn't it? If it went up the other way, it would have been a parabola. Okay, do you guys see something like, not an isotope, we don't really consider that here, but we do see something like bacteria growth. Do you guys see bacteria growth right here? Growth of bacteria starts a little slow and then it accumulates faster and faster and faster. That's why incubation period is usually 2 to 3 to 4 days. You get sick really by the time you actually feel it. You're about 2 or 3 days out. Stomach bugs the same way.
Stomach bugs triple.
Yeah.
It takes so much less time.
So got that. Let's see, population growth. Anybody see population growth here as well? Of something, right? Not a bacteria, but any kind of thing.
Specifically humans.
Yeah, anything that goes up exponentially.
Well, since 1970, we've almost doubled our population.
Right, it's fun to see a world population chart. It's kind of interesting to see. Okay, we're good, guys. Real quick here. So now the question is this: what happens if instead of it being a positive value inside the exponent, what happens if I switch it to a negative? X to the negative x. Real quick here, I'm going to take guesses. What do you guys think is going to happen? Just real quick here, Noah. Upside down. It's going to flip like this, go down. That's cool. That's good. Any other guesses before we do it? It's going to happen to this guy. No guesses. Thank you, Noah, for volunteering. At least guess. So.
This doesn't work.
Yeah, that was Noah's guess. Flipping the other way. So I'm going to go. Oh, good. Go ahead.
Y-axis?
Across the way. And how come you say that?
Well, because when we have the negative exponent, it turns into a small positive number. And then we have the- Seeing something, but I don't know. how
Yeah,
to
very
explain it
good.
yet.
Very good. No, that's perfect. Sometimes it is that way. So, Lily and Abby, good job. Good job in seeing it here. So, and we'll take a look at it. Just a bit. So,
Yeah, because it's the negative,
yeah, it's gonna be a negative of a negative, huh?
looks the positive, so then it would just switch ways.
Okay. Oh, sorry, 3. Keep on writing 8, but it's gonna be. So this guy's 8 now. Okay. So if I go like this, 2 to the negative of a negative 2 means 2 to the second, which is 4. Okay, the negative of a negative 1. And you know what? I see a pattern here already. Why do I do this when I see patterns? What's the next number gonna be? 1. Next number? Next number? Next number? Can you graph it? Go for it here. Okay, as you guys are doing that, I'm going to look ahead just real quickly here. All right, hopefully we saw this here. So now this guy's up at 8. Come on, there it is. There we're 1, 2, 3, 4. We're at 2, 1, 1/2, 1/8, 1/4, 1/8. Okay, so Yeah, it was flipped the other way, but it was flipped across the y-axis. So Abby and Lily, good job on that one. Noah, thank you for participating. You get like a participation award. Okay, let's jam because we got to finish up this here. So we got the graphs here. Oh, you know what, real quick here. I do have to show you this real quick. On your calculators, can you guys punch in -2? In fact, real quick, let's talk about this before we get to the next pieces here. So when we say 2 to the 3rd power, right? We're saying 2 times 2 times 2, right? Right. That's easy enough here. So if we do -2 to the 3rd power, that's easy enough. That's -2 times -2 times -2, which is -8. Are we good there? Cool. So on your calculators, punch in -2 in parentheses. Make sure it's in parentheses. -2.
That's what assumption I'm saying that I brought my.
-8.5641.
Ooh, okay. So just so we are careful here. So if you plugged it in like this, you got to put in the parenthesis and hopefully you punch this like this into the calculator. What do you guys get?
Non-real.
Mine said error.
Error. All right, you should say error because there is no way to do that problem whatsoever. There's no way to do pieces of negative numbers there. You good? If you did it like this, -2 to the power of 3.1, that's easy, right? Because you're saying this, you're saying, I'm going to take 2 to the 3.1 power and then stick a negative in front of it. We're good? But you can't have negatives on the inside of pieces of, or decimal pieces of exponents. Does not work. Okay, so
So the answer is just not possible.
not possible, yeah. So just kind of be mindful of when you get that stuck, don't start throwing your calculator across the room. Just means that you put a negative there, which should not be. Okay, so real quick here, let's do a rundown. This is on page, I don't want you guys to write all this down. This is on page 220. And we just covered it in the graph here. So whenever A is a positive number, and notice the domain on these guys are always from negative infinity to positive infinity. I can plug in whatever number I want. The range, notice we never hit zeros. Oh, sorry, we never hit negatives. We actually also never hit zeros. So the range for this is just positive numbers. We saw that on the graphs. This little intercept is very important, 0, 1. And then also, do you guys tell me if you agree? These guys are increasing always, is that right? It's always going up. It's always doubling, or it's always tripling, or quadrupling, whatever it is. And then Noah picked out the fact that if you go to negative infinity, the graph itself gets closer and closer to the x-axis. And we say that this is continuous. Okay, that's the first graph we made. The second graph we made, still the same stuff. It just goes down instead of up. So domain, I can plug in whatever I want. It's still above the x-axis. That same intercept is still there. It's going down this time. And now as it gets closer to the positive x-axis, it gets closer to 0, and it's continuous. We're good? Just for us to have that vocabulary in our mind. There, okay. So that's one piece. We just defined the exponential function, we graphed them, and let's see if we can solve some of them. So we're gonna solve just 2 real quick ones here. And the way we solve them is we have to have the bases exactly the same.
What does that say? 'Cause I'm sorry.
Sure. It just says using the 1-to-1 property.
Yeah, no.
Oh, got it. 9 equals 3 to the x plus 1. All right, how do we solve these here? We have to have the bases exactly the same. That's one way to solve it. Okay, so we got ourselves 9. 9 is what? 3 to the 3 to the second. This is 3 to the x plus 1. Once the bases are exactly the same, we just now have to get the exponents to be exactly the same. Is that true? So once the bases are exactly the same and the exponents are the same, we got ourselves the answer. So notice we got one thing here, right? The bases are now 3s. So now let's do this here. Now let's think about, when does x plus 1 equal give me a 2? When does that happen? When x equals 1, yeah, subtract 1 from that. Perfect.
So I learned something about infinite that's weird.
One second, now, let me just finish up this. So notice real quick, if that is true, let's go back a little bit here. If that's true, this is 3 to the 2, and this is a 3 to the 1 plus 1, which is 2. We're good? So notice the bases were the same. We just had to get our exponents the same. Answer to this one is just x equals 1. Okay, a little tougher one because it has a fraction inside it. So can you guys try it yourself? Go.
What does it say?
It has 1/2 to the x equals 8. So hold on real quick here. If I'm trying to take the reciprocal of 1/2 to make it a 2, am I still trying to make it a reciprocal? Real quick here, let's go back over here. Remember how I said that 2 to the negative 1 is 1/2 earlier? So what would happen if I want to take the reciprocal of 1/2? What would that be? I need a negative number. So what would 1/2 to the negative 1 going to be? 2. Absolutely. So notice this little guy just flips it across, right? So what I want to do is I want to flip a 1/2 and make it a 2. If that happens, I give myself this. Are we good? So, you know? Oh yeah, but 8, yeah. I just flipped this one right here. That's all. That's me flipping that. But yes, 8 is the same thing as 2 to the third.
So then x equals -3.
Perfect. Yeah. So my bases are the same. That's great. Therefore, I'm going to just work with my exponents now. Negative x equal to 3. Therefore, x is equal to -3. Whoa, and my pin is good. Okay, are we good there? So get bases the same, then get exponents the same. That's how we solve these problems. Okay, this was just a quick aside right there. What we want to do is we want to be able to now use transformations to graph this stuff. Okay, so remember how we did the transformations with parabolas? Remember we shifted over to the right and then we shifted up. We sometimes had a vertical stretch, sometimes had all the good stuff. You guys remember that? I know, whole last year, I understand. But let's try it.
You went very like quickly.
Everything is lost. One second. Nope, that's not what I wanted. Okay, I don't have my mouse with me here, so it's just doing whatever it wants it to do sometimes. So let me do this here. I'm just going to add a new slide here real quick. Boom. There. Okay, better. All right, you guys talk to me. What example are we on? What did it say? That was example
That
4,
was
I think.
4.
Okay, so example
4B.
5. Graph for me. Let's do, how much time we have? 3x plus 2. So notice, I'm going to take it in 2 steps here real quickly here. So, yeah.
Sorry, is the +2 part of the exponent or?
No, it's
No,
off to the
okay.
side. It's just adding 2. So you guys talk to me here. In previous times, what happened if we had just a +2 at the end of a function, all the way at the end?
Shifted it to the left to the smallest.
To the line goes up, right?
Yeah, at the end, if it's all the way at the end, you're just shifting the whole entire function up or down, right? So shifting up would mean, if it's inside the function, that's when it shifts inside and out, to the left and to the right. So real quick here, we need to graph 3 to the x. So think about, just real quick here, think about what does just 3 to the x gonna give us? I know we haven't graphed that function yet. So -3, -2, -1, 0, 1, 2, and 3. So 3 to the -3, what's that going to give us? Let's see, that's going to give us a reciprocal of 3. Anybody 3 to the third power? 3 times 3 times 3? That'd be 3 squared. 27, okay. 127. Ooh, that's small. Abby did this one already here, so that's his 1/9. 3 to the -1 means 1/3. Hey, this is just going up by 3s now instead of 2s, that's all. So this is 3 to the 0, which is 1. This is 3 to the 1, which is 3. 3 to the 2, which is 9. And 3 to the 3, which is 27. So I have that function. So normally what we do is we graph dots and then we move those dots up to give us the last function. So I got myself -3, -2, -1, 1, 2, and 3. Okay, the only other thing is I'm not going to graph all the way to 27. I just know which direction it's going to go, not to 27. I may graph up to 9, that's fine. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I'll graph up to 10. I'll be gracious. Notice my scale is off though, right? Notice my x-axis is expanded, my y-axis is condensed. So this is 1/27. It is tiny, tiny right here. And then I have 1/9, which is still tiny, tiny. Then 1/3 is just barely above. And then this guy again, 0, 1. I've seen that before in my base 2 graph. So this guy's gonna go 1, 2, 3 up. This guy's gonna go all the way to 9, and then 27, forget that one. Okay, what I want to do is I want to be able to move this up 2 units. Is that right? So let's move this up 2 units. So if that's the case, I give myself 1, 2. It's just barely above 2. Again, barely above 2. Tiny bit above 2. It hits a 3. And this one now hits a 5. Is that right? It hits, let's see, this is 1, 2, 3, 4, 5, right? And this one hits an 11. I'm going to stop there. So I'm going to graph this guy. Okay, boom. Are we good there? So again, I'm going to just set that up for you. Let me just check the homework real quick. And then what the more complicated ones on the homework, they I just say use a graphing utility and graph this. Okay, so that's kind of they want to do. So now let's graph it using a graphing utility. I'm going to eat the function is here. All right, so let's graph this guy here that we had. So y equals, and then we have ourselves 3 to the power of x plus 2. Okay, everybody good there? And graph it. Let's see what happens here. That sounds like the graph that I have. I notice it just went up 2 units, right? looking at the time here to see what I can finish up, because we won't finish up exactly all of it here when we went to one. I do have to give E, yep. Okay. We're gonna be almost done with 3.1, but not quite here. We can actually graph, let's do this here. Graphing exercise 6 using a calculator. Graph, so using a calculator, graph for me this function right here. Whoa, that gets really crazy, isn't it? 1.08 to the 5x. So all yours, try it yourself first. Okay, boom. Hopefully you guys did that already. Let's see, I'll go back to here. 1.08 to the power of, and real quick here, yeah, we've talked about this before, right? This is your power button right here. It's above the division problem, division one. And this one you need parentheses now because you're putting 5 in the x inside there. So 5x as your exponent, and that parenthesis holds all that in the exponent. And let's see what happens here. A little bit slower, huh? Just a little slower. Still, does it look like an exponential function? Climbs up or climbs down, which are the ways here? Okay, so with time remaining here, let's do this one here. So there is a one very special base that we use. It's called the E function. So let me jam to this right here. I'm not going to do that right here. So this guy, so it's called the natural base. Natural base is because, you know how we talk about population of bacteria, right? The E function, that base, is almost like it fits naturally into the way certain things grow. And so that's the growth function. Even in economics, it's the funniest thing. When we talk about money, it's still, we use E because it relates to how we think about the economy, how things grow in the economy. It's the strangest thing. Economy. Okay, so E function, just like pi. Anybody tell me what is pi? Ooh, hold on, trivia question. What is pi equal to?
3.14159.
Hold
on. No.
See if they're wrong, I will follow.
Pi is equal to what?
Is it just something of a circle?
It's this, it's the radius. No,
Very
isn't
delicious
it the X value? Isn't it the X value of the radius?
Oh, wow, here it is, ready? It's the circumference divided by the diameter of any circle whatsoever. Now, I think the question you guys were answering mine is, what is it? What's pi approximately?
No, I said, and it goes on and on after that, after.
Say again? Pi is equal to pi, yes. Approximately 3.14. Noah, did you have more digits? Go ahead to add. I'm going to stop there. Whew, okay. So the number E is approximately 2.71828.
The number E.
It's the number E. Okay. All right. And so with that, we're going to use that as the base. So we're going to start graphing using that as the base.
I spent way too much time in fifth grade memorizing pi.
It shows.
At one point, I know 100 digits. Now I know like.
Anyways, you guys have a great day. Let's see. Oh, as far as homework is concerned. Homework, you guys can get up to number 25. So up to number 25 on the homework. No.
whenever I had free time, I
Sure.
would memorize pictures.